All right, let's dive in. Today, we're talking about two super simple properties of matter that, believe it or not, secretly run our entire world. From the biggest skyscrapers to the tiniest gadgets, it all comes down to density and springs.
So, to get us started, here's a little puzzle for you. What on earth could a giant skyscraper possibly have in common with the little spring inside a clicky pen? I mean, one is massive and totally rigid, the other is tiny and, well, springy. The answer is actually pretty cool.
Turns out they're both built using the exact same simple fundamental rules of materials. Seriously. And once you understand these rules, it's kind of like getting a peek at the universe's own instruction manual.
So, to really get a handle on our world, we have to ask a really basic question. What is all this stuff actually made of? We're going to unpack the two key properties that define literally every material you can think of, from the air we're breathing to the phone in your hand.
Our first building block is density. You can think of it as a material's own unique fingerprint. It answers a really simple question. For any given amount of space, how much stuff is actually crammed inside? Now, the official scientific definition is that density is the mass of a substance per unit of its volume. It's just a super precise way of saying how compact, how tightly packed that matter really is. And this is the formula that makes it all work. That first symbol, it looks like a P, but it's actually the Greek letter rho, that stands for density. And to find it, you just take an object's mass and you divide it by its volume. Mass over volume. It's a beautiful, simple relationship.
Okay, a formula is one thing, but how does this work in the real world? How do scientists and engineers actually figure out the density of something, whether it's a brick, a glass of water, or, a chunk of gold?
Well, there are three classic ways to do it. For a nice, regular shape like a cube, it's easy. You just measure the sides to get the volume, and then you weigh it. For a liquid, you can use a measuring cylinder. But for a weirdly shaped object like a rock, you have to get clever. You weigh it first, then you dunk it in water. The amount the water level rises is the object's volume. It's such a brilliant little trick. And when you start measuring, you see this absolutely huge range of densities. Air is incredibly light, right? Just 1.3 kilograms for a whole cubic meter. We use water as our baseline. That's 1,000. But then you get to something like gold, a staggering 19,300. This is exactly why a tiny gold bar feels so surprisingly heavy when you pick it up. And this chart just puts it all into perspective, doesn't it? I mean, the bar for air is so small you can barely even see it. Water is our nice middle ground. And then look at gold. It's in a completely different universe. This one property, density, is what makes some things float and other things sink. It's why a hot air balloon goes up. It's fundamental. Okay, so we've talked about density, which tells us what a material is, but now let's move on to our second building block, which tells us how a material behaves. We're going to talk about stretchiness, and the golden rule for that is called Hooke's law.
So, picture this classic experiment. You hang a spring, you measure its length, and then you just start adding weights to it, one by one. And each time you add a weight, you carefully measure how much longer the spring gets. It's a really simple idea, but it led to an absolutely profound discovery.
Because this is what you find every single time. When you plot the force you've added against how much the spring stretched, you get this beautiful, perfect, straight line. It's not random at all, it's completely predictable. If you double the weight, you get exactly double the stretch.
This incredibly predictable relationship was discovered by the brilliant 17th century scientist Robert Hooke. And his law basically just says what we saw. The force you need to stretch a spring is directly proportional to how far you stretch it. Double the force, double the stretch. It's just so beautifully consistent.
Now, the steepness of that straight line we just saw, that has a special name. It's called the spring constant, or just K. And you can really think of K as the spring's personality. A really high K means you've got a super stiff spring, like in a car's suspension. A low K means a soft, stretchy spring, like the one in your ballpoint pen. But it gets even more interesting because we're not just talking about stretching. We need to look at how springs combine and how they actually store energy.
So what happens if you combine springs? Well, if you put two of them side by side, that's called in parallel, they actually share the load, and the whole system gets stiffer. But if you connect them end to end, that's in series, the whole thing becomes stretchier because each spring's extension just adds up.
Now think about this for a second. When you pull back a bowstring or you stretch a rubber band, you're fighting against its force, right? You're doing work. But that work you do doesn't just vanish into thin air, it gets stored inside the material as potential energy.
And this illustrates it perfectly. Remember our straight line graph? The energy stored in that spring is exactly equal to the area of the triangle underneath that line. It's this incredible visual link between force, distance, and energy, all in one simple graph. And that leads us right to this neat little formula. The elastic potential energy is simply 1/2 times the force you applied times the extension. This is the energy that powers everything from a kid's toy catapult to the heavy-duty shock absorbers in a mountain bike. So, let's take a step back and tie all of this together. We've looked at density and we've looked at elasticity. They seem like two simple concepts, right? But they are the absolute foundation for so much of the complex world that we see all around us. So here's the final takeaway. Density tells us about the fundamental makeup of a material. How much stuff is actually in there. Hooke's law, on the other hand, tells us about its character, how it's going to react when you push it or pull it. One describes being, and the other describes behaving. An engineer uses these two rules to choose a dense, rigid steel for a skyscraper and a completely different, bouncy kind of steel for the spring in your pen. They're two of the most fundamental building blocks of our world, and it really makes you wonder, what other simple, elegant rules like these are out there, just hiding in plain sight, waiting for us to notice them?